Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about the method of singular perturbation in order to solve the algebraic system of algebraic differential and system of differential equations. So we start without waiting and I will highlight this method of singular perturbation straight away using an example. So the idea is, let us look at an algebraic equation. To begin with, we start by solving an algebraic equation. So we have to solve epsilon x square plus 2x minus 1 is equal to 0. Now for just a few seconds, let us note the type of equations this time we are solving. Notice that now the small parameter epsilon is multiplied with the term of the highest order. So this is the term with highest order. And earlier we had epsilon, the small parameter, was not multiplied with the term of the highest order or the highest derivative, right? So that is the sure shot way of recognizing whether a problem needs to be solved using the method of regular perturbation or singular perturbation. If the small parameter multiplies the term with the highest order, then that problem is the customer of the singular perturbation method. Otherwise, it is the customer of the regular perturbation method. So let us now try and start solving this problem. So we see that again we try to separate out the terms without epsilon and the terms with epsilon. So we see that we have epsilon x square is equal to 1 minus 2x. So on one end we have a parabola epsilon x square. So this is my parabola, and on the other hand we have 1 minus 2x, right? And we see that the 1 minus 2x will be as follows. So of course 1 minus 2x, it cuts the x-axis at x equal to half, and we expect that there will be two roots, let's say R1 and R2. So visually we can confirm that the roots will have the following characteristics. R2 will be less than half, because half is the maximum point at which this straight line cuts the x-axis. So R2 will be less than half, and R1 will be less than 0. So R1 is negative. In fact, we will see that as epsilon goes to 0, this root R1 goes to negative infinity, right? So now suppose we solve using regular perturbation. Let us see what happens. So using regular perturbation, let us see what happens. So x is x naught plus epsilon x1 and so on. So this is the regular perturbation method. And if we plug this expansion into this term, we get that this is epsilon x naught plus epsilon x1 and so on square plus 2 x naught plus epsilon x1 minus 1, this is equal to 0, right? So we are looking at a term with epsilon power square. So we have just used the regular perturbation expansion for the unknown x. So now if we start to solve, so order 1 epsilon to the power 0, we see that the equation is 2x naught minus 1, where this is the term 2x naught and this is minus 1. So this is set equal to 0. This will give us that x naught is half. And then order epsilon term, we will see that the terms we are getting is x naught square plus 2x1 and this is set again equal to 0. From here, if we plug x naught equal to half, we see that we get x1 is equal to minus 1 by 8. And if we do a two-term expansion, we see that x comes out to be half minus epsilon by 8, and which we can clearly see that we have got root number 2, which is less than half. But what happened to root number 1? It turns out that the regular perturbation was able to successfully identify one root, which is the finite root, or the root which is close to half. The other root which is escaping to negative infinity is something which is not captured by the regular perturbation. So that is why now to find the other root, we have to use the method of singular perturbation, and let us see how to apply that. Okay. So then let us now start with the method of singular perturbation. So the idea is now the singular perturbation relies on the fact that the highest order term is a multiple of epsilon, right? So which means that we are going to assume a solution of the form x bar, which is x over epsilon to the power gamma. Why? Because we are going to rescale the solution so that the epsilon dependence is somehow gone, right? So we are going to rescale our variable so as to take care of the epsilon dependence in the highest order term, right? So this is the rescaling factor. Now we will assume that gamma is positive, otherwise there is no point in division by epsilon to the power gamma. And then if we plug it, let me call this 2, if we have the equation as 1, so if we plug 2 in 1, we see that we get epsilon 1 plus 2 gamma x bar square plus 2 epsilon gamma x bar minus 1 is 0. So after plugging this rescaled solution, we get the following new equation. Let me call these three terms as term number 1, 2 and 3. So now notice that term number 1 has to be kept. It cannot be taken to 0, otherwise the whole idea of otherwise we won't get the second solution. If we choose gamma in such a way that term number 1 is gone, then we will only get one solution, which is what we found out earlier using regular perturbation. So term number 1, so the first observation is we need to keep term 1. We need to keep term 1, otherwise the highest order term is gone and we are back to square 1. So then the only problem now is on the right hand side we have 0. So if we keep term 1, it has to be balanced and cancelled with either term number 2 or term number 3, right? Now notice that since gamma is greater than 0, so we have that this term number 2, term 2 is the order of term 2 is less than the order of term 3. Term 3. Why is that? Because term 3 is epsilon to the power 0 term and term 2 is epsilon to the power gamma term, and we have taken gamma to be positive, right? So we have term 2 to be lower order than term 3. So we are going to balance term 1 with term 3 so as to expecting that the lower order term will appear at the next approximation, right? So the idea is that we balance the term that we need to keep, term 1, balance term 1 with the other highest order term, and this is going to be term number 3. And if we do that, we get that the order of epsilon, which is 1 plus 2 gamma, is 0, or we have that gamma is minus 1 half, right? And now what we see is term number 2 is, well, so if we had so if that is the case, highest order, we have assumed that the highest order term is this, term number 3, right? And we are facing some problem here that if we had balanced term number 1 with term number 3, then let us see what is term number 2. So term number 2 is of order epsilon to the power minus half, right? So so that is certainly of order which is higher than order epsilon to the power 0. So what we are getting is the order of term number 2. The order of term number 2 is greater than order of term number 3. So something strange is happening, right? Let us for the time being assume that we are not going to assume that gamma is positive for the time being. Okay, so we want to choose gamma in such a way that there is no inconsistency. Right now we are having an inconsistency, okay, some sort of a contradiction. We assume that this term number 2 is order is less than term number 3, but we got exactly the opposite. So let us now try and balance term number 1 with term number 2. So so this was exercise 1. So case 1, we balanced term number 1 with term number 3, we got an inconsistency. So let us now look at the other case. We balanced term number 1 with term number 2, and we see that we are going to get so the order of epsilon 1 plus 2 gamma is equal to gamma. Gamma is the order of epsilon in term number 2, and from here we are getting gamma is minus 1, right? So gamma is minus 1, and now the entire idea was we were balancing term number 1 with the term of the highest order. So since we were balancing with term number 2 in this case too, which is correspondingly we are assuming that that term number 3 is of lower order than term number 2. So we are assuming that term number 3's order is lower than term number 2, and we can check that in this case, in term number 2's case, this is of order epsilon to the power minus 1 because gamma is minus 1, and term number 3 is of epsilon to the power 0 because it is 1, right? So certainly we have found that we are in consistence. We have found a consistent value of gamma. So this value of gamma is acceptable, right? So let us now tabulate what we have seen. So we are trying to do a balance of the terms. And we are trying to find a condition on gamma. And we are trying to figure the consistency in our assumption, consistency check, and we want to figure out what is the conclusion. So in the first case we saw that we tried to balance term number 1 with 3, and assuming that term number 2 was of order much less than either 1 or 3, and what we found was the condition on gamma came out to be 1 plus 2 gamma is 0, or gamma was minus half, and the consistency check was that term number 1 and 3 was of order epsilon to the power minus half, and term number 2, well, term number 1 and 3 was of order epsilon to the power 0, 0, and term number 2 was of epsilon to the power minus half. So certainly the conclusion is that the original assumption was wrong and the conclusion is inconsistent. So similarly, if term number 1 is of order, we assume the equality of term number 1 and 2, and with the assumption that term number 3 is of order much less than 1 or 2 both, then we get that the condition on gamma was 1 plus 2 gamma was equal to gamma, and from there we found gamma was minus 1, and in this case term number 1 and 2 was of order epsilon to the power minus gamma, and term number 3 was of order epsilon to the power 0, and we see that term number 3 is of lower order than 1 and 2. So this was a consistent setup. So the final answer is that gamma is minus 1, and now x bar comes out to be which we assumed x by epsilon to the power gamma was equal to epsilon times x, because gamma is minus 1. Okay, so then if we plug this, if the original equation was this one, let me call this equation number 3. So if we use our assumption 2 in equation number 3, so use in equation 3, we see that now our new equation is x bar plus 2x, x bar square plus 2x bar minus epsilon is equal to 0. Most crucially, now epsilon has now been removed from the highest order term to some lower order terms. And now again, to solve this problem, since it doesn't show the singular perturbation characteristic, we can use regular perturbation expansion to solve for x bar. So we can assume that x bar is x0 plus epsilon x1 and so on, and if we plug the solution, we see that x bar is x0 square plus 2x0 x1 epsilon and so on plus 2 x0 plus epsilon x1 and so on. So this is the substitution here. This one is the substitution of x bar square and minus epsilon, this is equal to 0. Right, and now we can start to figure out the solution for order epsilon to the power 0. We see that x0 square plus 2x0 bar is 0, or x0 comes out to be negative 2 or 0. There are two solutions to it. Now similarly, for order epsilon to the power 1, we see that the equation is as follows. And now depending on x0, we will have two different values of x1. So if your x0 comes out to be minus 2, then x1 comes x0 bar, then x1 bar comes out to be negative 1 by 2. And then what we have is x comes out to be 1 over epsilon. So x is x bar by epsilon. So hence x comes out to be 1 over epsilon times negative 2, negative 1/2 of epsilon. Right? So negative 1/2 and negative 2. So now if we multiply this by 1 over epsilon, we will see that the solution, again, this is our second root R2, which is close to 1/2 or which is close to negative or close to 1/2. Well, we'll have to see. Right. So, this is the root 1 that we were searching. Sorry, this is the first root we were searching. And then if we take x0 bar to be equal to 0, that is the second choice, we get x1 bar equal to half, and in this case x comes out to be 1 half minus epsilon by 8 and so on up to 2 terms. So notice that this is my second root R2, which is the one which was close to half. So singular perturbation has been able to provide us with not only the root that the regular perturbation was giving us, that is R2, but also the other root R1 which was earlier missing and which was escaping to negative infinity as epsilon goes to 0. So the singular perturbation, we do not have to start with regular perturbation, but in problems like these we start with singular perturbation and we will get both all the solutions to the problems. Okay, so then let us try to solve some differential equations using the method of singular perturbation. So the problem that we have now is that of the boundary layer. The boundary layer problem. So let's not worry too much about the words here, but essentially we are trying to solve a second order ordinary differential equation subject to some initial condition or boundary condition. So we have a singularly perturbed ODE, and we see that this is epsilon y double prime plus 2y prime plus 2y is equal to 0, and x is between 0 to 1, and the boundary condition is y of 0 is 0 and y of 1 is 1, right? So this is what we have. So to find, well, one way is this is a simple second order ODE, so we can find the exact solution. So to find the exact solution, let us assume y is equal to e to the power rx, and that is going to give us the solution of the form when we plug this form of y, we are going to get an algebraic equation of second order, and that will provide us with two roots r plus minus, which is minus 1 plus minus square root 1 minus 2 epsilon by epsilon, right? And that are the two roots. Okay. So now what we would like to see is, so of course the general solution to the problem, the general solution is y of x is equal to c1 e to the power r plus x plus c2 e to the power r minus x, right? And if we were to use the initial condition, we will see that this is also equal to e to the power r plus x minus e to the power r minus x by e to the power r plus minus e to the power r minus, right? And we see that this is using the initial the boundary condition. If we were to plot this function, we see that if we plot this function y versus x, we get the following plot, right? And so this is the x-axis, we get the following plot. One thing I would like to highlight using this plot is that the variation of this solution y is very sharp near the boundary x equal to 0. That is, the function changes more rapidly near x equal to 0 than near x equal to 1. Right? So the function variation is slower near the other boundary x equal to 1. Right? And so what have we got? So which means that we have the so-called presence of boundary layer at x equal to 0. So boundary layer implies that we have a very sharp variation of the solution near one boundary. That is when we expect the formation of boundary layer, and that numerically when we want to solve a problem involving boundary layer, we have to take a lot of grid points and resolve it more accurately because of the sharp variation. So then, so if we sketch, so that is the point. So now, which means that because of the sharp variation of the solution near x equal to 0, we expect that the solution will have a singularly perturbed the form near the boundary layer x equal to 0. So we have a singularly perturbed form near x equal to 0 because of the boundary layer, and since there is no boundary layer at x equal to 1, we expect that the regular perturbation will work nicely because of the slow variation of the problem, right? So then we are going to call this singularly perturbed solution near the boundary layer as the inner solution. This is the inner solution, and we will call as the more relaxed variation of the solution outside the boundary layer as the outer solution. So the general rule of thumb is the outer solution will be solved using regular perturbation, and the inner solution will be solved using the singular perturbation. Okay, so then, so if we assume so this is the step 1 here. So we are trying to solve the outer solution near x equal to 1. That is the regular perturbed solution. So we can assume that y has the regularly perturbed form y0 plus epsilon y1 and so on near x equal to 1 with the boundary condition y0 at 1 plus epsilon y1 at 1 and so on. This is equal to 1. Right? We are going to use only the boundary condition for the outer solution. Right? This is the outside the boundary layer expansion. So y of 1 is 1. So we are using that boundary condition for the outer solution. So now we plug this form into our equation, the original equation, and we start to solve for order epsilon to the power 0. We see that this is 2y prime naught plus 2y0 is 0, or y0 1 is 1, and order epsilon to the power 1 y0 is, well, if we solve this with this initial condition coming from the expanded initial condition here, we get that y0 is e to the power 1 minus x, which satisfies the condition at x equal to 1. Okay, so then similarly, if we solve, well, this was order epsilon to the power 0 solution here. So now if we solve order epsilon to the power 1 solution, we get that the equation is y0 double prime plus 2y1 prime plus 2y1 is 0, with y1 of 1 is 0, and or we get the solution to be y1 of x to be equal to 1 minus x e to the power 1 minus x by 2. Okay. So which means that so what we have now is, so we have already found y0 and y1. So we are ready to write the two-term expansion. So near x equal to 1, y is given by y0, which is e to the power 1 minus x, plus epsilon by 2 times 1 minus x times e to the power 1 minus x, and so on, plus order epsilon square term. So this is my solution outside the boundary layer, or the outer solution. Right now, now we have to figure out the solution in the boundary layer, or the so-called inner solution. So now to find the inner solution, let us assume, so this is inner solution near the boundary x equal to 0, right? So if we introduce the boundary layer coordinate, we have that x bar is x over epsilon to the power gamma. So this is what the solution we are assuming, and this is going to be x. Well, so this is my initial assumption for the singularly perturbed solution. Now if we plug it into our equation, so use in our boundary layer problem, we are going to get, note that if we have derivatives of this form ddx comes out to be 1 over epsilon to the power gamma times ddx bar. So that is the relation between the derivative in the old variable and the derivative in the new variable. Similarly, if we have the second derivative, this is related to epsilon to the power 2 gamma dd x bar square. Okay, so then if we plug everything into our ODE, the boundary layer ODE, we get the following new equation: epsilon to the power 1 minus 2 gamma of y bar double prime. Well, let me call this as y, capital Y double prime. What is capital Y? Capital Y is y at x bar, that is in the evaluated with the new variable x bar here. Okay, so then plus 2 epsilon minus gamma y prime plus 2 y prime y is equal to 0. Okay, so then what we have is that this is term number 1, this is term number 2, and this is term number 3. And what we have is that we of course we need to retain term number 1. So term number 1 could be either equal to term number 2, or term number 1 could either be equal to term number 3. And again, we can use the consistency check. We can start with case 1. Case 1 is when 1 and 3 have the same order. This is our case 1. And then we see that in this case 1 minus 2 gamma is 0 because term number 3 has order epsilon to the power 0. Or we see that gamma comes out to be half, and then in this case term number 2 is going to be epsilon to the power order epsilon to the power minus half, and that is certainly going to be greater than term number 1 or term number 3, right? Which are both order epsilon to the power 0. So we have found an inconsistency, and which means we cannot compare term number 1 with term number 3 because we have an inconsistency. So then we will choose the other case, that is we are going to match term number 1 with 2, and in that case we have 1 minus 2 gamma is minus gamma, or gamma is 1, and in this case term number 3, which is of order epsilon to the power 0, is going to be less than term number 1 or term number 2, right? So that is going to, so this is consistent. So we have arrived at a choice of gamma. So gamma has to be equal to 1. We plug it into our expansion. Gamma is equal to 1. And we see that our new equation is as follows. Our new equation star. So star reduces to the following. We have the new equation y double prime plus 2y prime plus 2 epsilon y equal to 0, and we see that so this is my y, and we see that y is going to be y naught plus epsilon y1 and so on. So y is this value. Okay. So y is of this form, and so here we are. So we are now changed. We have now changed the singularly perturbed problem into a regularly perturbed problem because epsilon has shifted from highest order derivative to lower order terms, and now y comes out to be. We are assuming a regular perturbative expansion form of y to be this, and now we can plug this y into this equation to see what is happening. So y now, the regularly perturbed solution for y now will be y naught plus all the higher order terms plus 2 y naught prime plus 2 epsilon y naught. This is equal to 0, and my initial condition is y of 0 is y0 of 0 plus epsilon y1 at 0 and so on. So this is the condition that we have to evaluate it at x equal to 0. So this has to be equal to 0, and then we can start to solve my my equations of order epsilon to the power 0. You see that this is y double prime plus 2 y naught prime is equal to 0, or y0 of 0 is 0. So my general solution is y naught equal to a plus b e to the power minus 2x bar, right? And with what we have is y0 of 0 is 0, and we find that this is my initial condition. So from here I get that y0 is a times 1 minus e to the power minus 2x bar, right? And what we get is that an approximate solution. So this is my y0, and we have found the inner solution y0 in terms of a constant which is a. So we have to figure out this constant a, and to do that we are going to match. We are going to do a so-called asymptotic matching, a matching. That is, we are going to match the outer solution at y, which is y0, the outer solution when we, so if we look at what we had, the solution of the form, so at the outer solution we have to take the outer solution towards the boundary layer, and we have to take the inner solution outside the boundary layer, and we have to match it at a certain point. So this is the outer solution. We match it at x tending to 0, and we match the inner solution at x tending to the inner solution at x tending to infinity, and the outer solution at x tending to 0. So basically the outer solution is taken to the left, the inner solution to the right, and we are going to get that. So we have to match y0 at 0 to y0 at infinity, and from here we get that a is equal to e. So we have found our constant a. So now we have actually found two solutions, one as the inner solution up to the leading order and one as the outer solution. So what is the net solution for the entire domain, inner plus outer? So it turns out we need to find the solution. We will have to do a composite approximation, that is, our y now has to be the sum of the sum of the outer solution plus the inner solution minus the double counting. See, in both inner and outer solution we have added the constant a each once. So we have to subtract at least one constant a. So we will subtract y0 of 0 or capital Y0 of infinity, either one of them, so that we avoid the double counting. So now this is going to be valid for entire x from 1 to 0 to 1. Earlier the solutions were separately defined at different layers inside and outside the boundary layer, but now this solution is defined in the entire domain, the composite solution. And if we plug in all these answers, we are going to get that y is equal to 1 minus e to the power 1 minus x, which is y0, plus 1 e times 1 minus e to the power minus 2 times x over epsilon, minus y0 of 0, which is e. So e cancels, and we are going to get that this is e1 minus x times minus e to the power 1 minus 2x by epsilon, right? So we have got the two solutions, e1 minus x and e1 1 minus 2x by epsilon, right? So what we have is the final solution here, and this is what the final answer in the entire domain looks like.